All right, everybody, it's about 4 o'clock. I think I'm gonna get started here tonight. Hello and welcome. I hope that you're having a good week so far and cruising through, getting towards the middle of the semester already. Feel like we just started. It does go fast, really does go fast sometimes. So let's see. Announcements wise, I don't have a lot for tonight. Just reminding you there's no homework due tonight. In fact, the next assignment is not due until Tuesday. It'll be covering basically everything we're doing this week. This past Tuesday, we talked about spanning sets a lot. Tonight, we're going to talk about linear independence. And then those two sections are kind of what the next homework is going to be on Tuesday. Also, if you want to stop by my office hours tonight, if you could do it on the earlier side, if you're going to come in person, I might try and leave a little early just since there isn't any homework due and I've got a bunch of exams to grade for my other class. So I have office hours starting at 8. I'll probably be gone by 9. So I'll try to log back in through Zoom after I come back from dinner, but I won't be coming back to the office tonight. Okay, so if you want to talk to me late night, check Zoom for me on that, and that'd be the best way to get a hold of me. But yeah, other than that, nothing major going on at this moment with any of the stuff that we're doing. So, does anybody have any questions about any of that? I noticed my grader was very fast with this most recent homework, which I was surprised by because the homework on subspaces takes a fair bit of writing. It's kind of long-winded. So be sure to look over that feedback and let me know if you have any questions about it. If you want to check with me about anything, you certainly can. I did post the solutions to it. That homework that you turned in on Tuesday is definitely not one you just want to sort of forget about, right? That was a pretty important set of skills that were being looked at in that assignment. So just definitely keep working at it. We're getting there, guys. We're getting through chapter 4. We're almost halfway through it already. So I feel like we're making good progress. Okay. Oh, I also wanted to mention, I pulled up the Canvas page here just to show you something. If you go to the files section in the Canvas homepage, I think I talked before about this folder that says special handouts on it. So I'm going to click into there for a second. There is a handout that is actually called spanning sets. So I wrote a little Reader's Digest version of sort of this section we've just been covering. It's only a 3-page document. But if you really want to get the bare bones summary of what are the things you're going to need to be able to do with spanning sets, this is not a bad thing to just have kind of in your back pocket rather than the whole entire stuff out of the book. So this is just a summary of it. I just wanted to let you know it is here. There's a lot of examples in here. So there's finding a spanning set for a subspace, right? That was certainly something that we had the 3-step, step A, step B, step C that we learned on Tuesday. So I've got examples showing that here. So finding spanning sets, obviously writing down the general form of an element in the space. These are all things that you guys are going to want to be able to do. So anyhow, I just wanted you to be aware that that is there as a sort of an extra thing that you can take a look at. Okay. So, but without further ado, I've got a summary of what we did on Tuesday right over here on the board to the left, and I want to bring that back into focus for us here as we kind of start today. We've been talking about forming a span of a set of vectors. Obviously, it's the main concept here. So we grab a set of vectors and we just take all possible linear combinations of them. And if we do that, we will be guaranteed of having a subspace of V. And there are as many different handfuls of vectors to grab as there are people in this room and then some. So we can make all sorts of subspaces, right? Every single one of us can make our own special subspace of whichever vectors we grabbed and making all of the linear combinations from that. Okay, so you can always do that. Now, it might be the case, we talked about this on Tuesday, it might be the case that by the time you grab your handful of vectors and form all of these possible linear combinations, you might end up with the entire big vector space V, the entire universe V out of that. So if that happens, then I meant to underline this, then those vectors that you grabbed are actually a spanning set for V, right? So a spanning set for V is just a set of vectors such that when you close them up under addition and scalar multiplication by doing their span, you get the entire vector space V out of that. Now, if you don't get V, that's okay. You just get a subspace of V, some subspace within the vector space V. But it's possible you could get the entire vector space V. That can happen. And if that happens, just to remind you again, if it happens to be the case that the entire big vector space V is spanned by this handful of vectors, V1 through Vn, then those handful of vectors are really important as building blocks of the entire vector space. In other words, everything in V is somehow buildable, expressible in terms of linear combinations of that set. So having a spanning set is a good thing, right? We would love to, for every vector space we ever meet, we would love to be able to say, hey, here's a spanning set for it, right? That's what we really would like. Okay, well, we also talked on Tuesday that there's a test that we can do to find out whether a handful of vectors really will be a spanning set or not. And you might remember I did a few examples of this in the second half of our class on Tuesday. You lay the vectors that you have grabbed into the columns of a matrix. Okay, so this is the first time this semester where we've been laying vectors up and down. Rather than filling out the matrix row by row, here what we're doing is filling it out column by column, putting those vectors into those columns, right? And what we're going to do, guys, is, if you remember, we need to augment this matrix with, well, with what is really an arbitrary random looking vector from V. And I chose to kind of use these little hashtag number symbols to denote that. So you'll see me, and I'm going to do it again tonight, you'll see me putting those number symbols into the far right column, recognizing that if that those could be pivots, right? Those positions of those number symbols might be pivots. And in fact, the test, the real test here, guys, this is what everybody's going to need to be able to do, is find out whether this matrix is consistent or inconsistent. If you can solve it without having a pivot go into the far right column, then we're happy. Then it's a yes, it is a spanning set. However, if this is an inconsistent system, which of course just means that a pivot has gone into the far right column in our ERO process, if that happens, then that's a no. That means then the vectors that you grabbed are not a spanning set for V. They'll still span something, right? They're still going to make a subspace. They just wouldn't be making the entire vector space V in that case. Does this make some sense? So I hope that I've kind of sold you on the importance of having a spanning set. This is a good thing. We have a vector space. We would love to find a spanning set for it. So I'm going to talk a little further about that now. Actually, I think I'm going to move this table so that it's not blocking the view here so much. Put this way over here for now. Sorry, I forgot my tripod for my camera here. Yeah, so I want to, think a little bit more about finding a spanning set for my vector space. Intuitively, the more vectors that you grab to begin with, a better chance that they will be a spanning set for V. Because after all, if you start with more vectors, then you get to make more linear combinations. And you're going to have a bigger sort of array of things that you can build out of that starting set of vectors. And so let me show you a quick example just to kind of get this going of something in a fairly easy context. Let's suppose I use R2. Just going to make a nice, easy example here. And I'm going to consider a set of vectors now. Okay, and maybe my first vector is going to be the vector 1, 2, and then my next vector is 3, 4, and my next vector is 5, 6. And I'm going to actually write dot, dot, dot here for a moment, and I'll come back to that in a second. But let's say we have some vectors that we've grabbed here, and we would like to do the sort of the test for spanning set, which I've got on the left board over here behind me. So the way this test works is we lay the vectors up and down, right? So the first vector 1, 2 goes like that. And then the next vector, which is 3, 4, goes like that. And the next vector, which is 5, 6, goes like that. Now, if that was all the vectors that I had, I would, draw my bar. Eventually, I would draw my bar, and then on the far right side of the bar is where I put those number symbols. And we would like the pivots to not make it over to those number symbols. Right? If one of these number symbols ends up being a pivot, that's inconsistent. That means we don't have a spanning set, right? So common sense would tell us, well, if we grab more vectors to begin with, we're more likely to have a consistent system. Because let's say I grabbed another vector. If I decide to grab 7, 8, right? Well, now that puts another column in here. And every time I take another vector, every time I decide to grab another vector, I'm building more and more columns on the left of this bar, right? If this matrix gets really, really, imagine that you grabbed 100 vectors, right? Well, then you would have 100 columns before you even get to these number symbols. And the chances that a pivot is going to make it 100 columns to the right is pretty low, right? So in that sense, the spanning set game is pretty simple. You want to span your vector space? Just grab a truckload of vectors. Just take as many as you want, right? Just grab a ton of vectors. That would certainly work. The more every time you put another vector into this set, you will be adding another column here. You'll be making your matrix wider and fatter, giving you a better chance that the pivots will not make it into the far right column. And it seems like an easy thing to do, right? So, of course, mathematicians are going to find a way to make this a little more challenging. And so here's the way I want you to think about the challenge that I'm going to put before you now. I would like you to imagine that every vector that you put in your spanning set costs you $1,000. You would like to span V, of course. That's the whole idea. We would like to have a spanning set. We would like this answer to be yes. But now I'm going to make a new wrinkle here, which is that you can't just grab a truckload of vectors and throw them in there and call that a spanning set because it's too expensive, right? It's going to be too expensive. So what we would like to do is get the cheapest possible spanning set possible. So what we're going to do here, the goal is to span, or sorry, let's just say it this way. The goal is going to be to find a spanning set for V that is as quote unquote cheap as possible. What I mean by this is using as few vectors as possible. This is going to be the idea. We don't want to grab wasteful numbers of vectors here, right? In fact, you might already see that if I want to span R2, I really don't need this vector. And so I could just cross this one off. And I don't need this one either. I could cross it off. I actually only need those first two. Because if I do EROs on just even this little matrix, 1, 3, 2, 4, you'll get a pivot. What will it be? You'll have a pivot there, and you'll get a pivot right here. I guess it's going to be a -2. And so you're already consistent. The system is already consistent, even with just 2 vectors. So why would you spend $4,000 to span R2 when you can do it with only $2,000, right? If you only need 2 vectors. This is the way I like to explain this concept. We would like get a spanning set that is as cheap as possible.
So
And
V3 and V4 are basically useless. Right?
yeah, they're kind of, they're redundant would be the word I would use. That you're talking about these vectors, V1, V2, V3, and V4. We don't really need to take anything more than just V1 and V2. So just make a note here. Just make a note here that the span of V1 and V2, just those two vectors, it's already the entire universe of R2. I don't need to grab any additional vectors beyond that. Okay, is this making sense? Well, there is a formal concept for this, guys. This idea of building a cheap spanning set, and the concept is linear independence. So I'm going to start this section here, 4.5. We're about halfway through chapter 4 finally, and this is called linear independence. Now, I'm going to abbreviate that usually because it's just too long to keep writing it. I'll be writing that as LI. And then slash, the other related term, which is sort of just the opposite thing, is linear dependence, which I will be abbreviating with LD. So section 4.5 is about LI and LD. And LI is sort of, LI is a good thing. This is what we would like. If the vectors are Li, that means we did not spend too much money. It was actually the best we could do. If the vectors are LD, this is kind of roughly speaking, it's a bad thing. It means that we paid too much money. So the 4 vectors that I've presented in this set here at the example would have been LD. But if I'm willing to remove the 3rd and 4th vectors and only keep the first 2, these 2 vectors alone are Li. Okay, see the difference? So just the first 2 are going to be Li, but if I took all 4 of these, that's bad. Those are LD. So if we're trying to get the cheapest possible spanning set, we're really looking for a set of vectors that is Li. So this is the game. We would like to span our vector space. We would like to find a spanning set for V, building blocks for V, but we want to do it as cheaply as we can, using as few vectors as we can. So with that in mind, I would like to write down the definitions now of what Li and LD mean, unless there's any other questions so far. This is just kind of the preview. This is just going to get you, hopefully, to understand what the world we're talking about right now. Okay, with a pretty easy example, of course, the vector space could be polynomials, it could be matrices, it could be anything. I just started with R2, since it's a relatively easy vector space. Let's make a definition, guys. Put this definition over here. A set, and I'm going to make this as a set again, V1, comma, V2, and so on, comma, up to Vn, is LD. So I'm going to explain what LD means here, linearly dependent, or dependence. If, here's the basic definition, at least one of the vectors in the set, right, at least one of those vectors can be written, if at least one of those vectors can be written as a linear combination of the others. Of some or all of the others. Can be written as a linear combination of some or all of the others. Saying it right, I'm just not spelling it right. Some or all of the others. There we go. That's the idea. That's going to be the idea here. Otherwise, if that's not the case, otherwise, my set V1, V2, and dot, 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 up to Vn is Li. So you got good, you got bad. They're the opposite of each other, and you can't be both, right? Any set of vectors will either be Li or LD, depending. Okay, and what's the crucial point? crucial issue is, can you write one of the vectors, at least one of the vectors, in terms of some or all of the others? Let me start with a really simple example of this, so we can kind of get the idea behind this. Let's say that my set of vectors was 1 plus x. So I'm going into polynomial universe right now. 1 plus x and 5 plus 5x. So we could take something like that. Do you think that does that look like that would be Li or LD? Looks pretty LD to me, right? Can I write one of these vectors? By the way, we can label these as V1 and V2. Can I write one of these vectors in terms of the other? Absolutely. The second vector is just 5 times the first one, right? So here, so this is LD. Sometimes when we have a linearly dependent set, we will be asked to provide a what's called linear dependency. In other words, show me what actually is the equation. In this case, the linear dependency would be this right here. V2 is equal to 5 times V1. Okay, so we could just write that down, and it would be pretty easy. Okay, so this is called, I should probably add this to the notes as well, guys. This thing I put in the box, this is called a linear dependency. And remember that is a bad thing. We already spent $1,000 for this vector. And then we went back and spent another $1,000 on this vector when we didn't need to. We could have just taken the first vector that we had purchased and multiplied by 5, and we could have made the second vector from the first one ourselves. We didn't need to go putting that second vector into our set, if that makes sense. It's one way to think about it. Okay. So you can imagine that what we would do in this situation, we realize, oh, we paid too much money for this. Let's go back for a refund or something, and get rid of some vector that's causing the linear dependency. So we're going to do that. We'll talk more about that here in just a little bit. Anyway, so far so good. I actually want to make a remark here that since this is a good example to illustrate this remark with. So I'm going to make a remark here, guys, in blue, because if you have exactly 2 vectors, which we do here, if you have exactly 2 vectors, then the issue of whether those vectors are Li or LD literally comes down to whether you can write one of them as a scalar multiple of the other. In other words, they would literally have to be scalar multiples of each other. This is only for 2 vectors, okay? So I'm going to just make this point. So given 2, you need to really hit that with some underlining. Given 2 vectors, V1 and V2, right? Then those vectors as a set, V1 comma V2, these vectors will be, let me just explain it as how it would be phrased for Li. Like, when would those be a good set of vectors? 2 vectors are going to be Li if and only if they are not, emphasize not, they are not scalar multiples of each other. Okay, if they are scalar multiples of each other, like this example, then they're going to be LD. Now, this is only for if you have 2 vectors. If you have 3 or 4 or 5 or more vectors, then that remark does not actually work. So be a little careful not to use this blue summary here. This is a nice fact when you have exactly 2 vectors, okay? But we can sometimes have a lot more than that. Let's do another example. Other questions so far? So far so good? Okay, let's come back over here and try to write down another example. It's maybe a little bit less obvious. this first example was pretty obvious, right? The second vector is obviously 5 times the first vector, right? Maybe it's not always quite that obvious. Let's do another example here. And I think I'm going to use polynomials again one more time. So I'm going to ask this one as a question this time. Is the set 1, comma 1 plus x, comma 1 plus x squared, comma 1 plus x squared plus x cubed, comma x plus x cubed. Okay, I got 5 vectors for you there. Is that set Li or LD? Remember, Li is a good thing. LD is, kind of think of it as a bad thing. Okay, so let's play with this for a second. So I could label these vectors. Here's v1, here's v2, here's v3, here's v4, and here's v5. So our definition that we have on the board over there is that these vectors will be LD if we can write one of them as a combination of the others. So looking at this set of 5 vectors, anybody have any thoughts about that? Can I write one of them in terms of the other? Yeah?
It's LD because V3 plus V5 equals V4.
V3 plus V5 is actually not equal to V4 because there's an X and an X which adds together to 2X. But keep thinking.
There'll be 3 variables.
We're going to get into all this issue of like, remember the running joke of everything in Math 250B is that the answer to every problem in this class is put it in a matrix. Well, so far today we don't have a matrix on the board, but we are very soon. There will be a way to answer this kind of question using a matrix in a moment. But I just want to what I'm trying to just do here with you guys is to show you that trying to figure this out kind of by eyeballing it is not that easy normally, right? You can't just have a handful. I mean, this one was very easy, but normally it's not that easy. It turns out though that if I take V2 minus V1, and then if I take V4 minus V3, you see V2 minus V1 is actually X, and V4 minus V3 is actually X cubed. And so together they make up V5. So let me just write that down. These are LD since V5 can be written as, I'm going to write it with some parentheses just to make it a little more obvious. The quantity V2 minus V1 plus the quantity V4 minus V3. So I've managed to write one of my vectors as a linear combination of some or all of the others. And again, this would be my linear dependency. We would consider that to be our linear dependency. Okay, does this make some sense? Edgar?
Like all or some, like if there was some way to rewrite that combination using only 3 of the vectors, it would still be LD.
It'd still be LD, yeah. And there's not just a unique linear dependency either. So I happen to write V5 in terms of the others, but maybe I could have instead, written V2 in terms of the others as well. That might be a different looking equation, but it would still be a linear dependency. So we're not saying that this is unique or anything like that. But what we are saying here is that $5,000 was too much for that set because we could have at least taken V5 and written it out of $4,000 worth of vectors instead. Jesus?
So in order to show LD, we don't really use every vector.
You don't. I could have added more vectors over on here on the end and never touched them. Yeah, that's exactly right. Yeah, good comment. Okay, so this first example, I was good with that. It's like, okay, I can see the second vector is just a multiple of the first. That's LD. This example is making me nervous now. I'm like, well, how am I going to be able to see these linear dependencies? Am I supposed to just sort of figure it out in my head kind of thing? It turns out we don't have to do that. There is a nice way to rephrase linear dependency in a way that we will then be able to put this whole question into a matrix. Okay, so I'm going to rephrase this this concept for you right here. I'm going to rephrase what LD means. Okay, I'm going to rephrase it in a little bit more friendly way. I'm going to try to write it in a little more of a friendly way. So I'm going to say it this way: this set V1, V2, and dot 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 up to Vn, we make this set of vectors, is LD if and only if. So I'm going to rephrase the definition. The definition is blah, blah, blah. At least one of the vectors can be written as a combination of some or all of the others. This is going to be a slightly more mathematical way of saying the same thing. Namely, there exists, so here we go, this is important. There exist constants. There exists constants, and these constants are C1, C2, all the way up to Cn. And now I'm going to give you the three most important words that I'm going to put on this right-hand side. There exists constants C1 through Cn, and here are the three most important words: not all zero. Okay, not all zero, such that there exist constants, not all zero, such that you can actually take C1 times V1 plus C2 times V2 plus dot, 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 plus Cn times Vn, like that, and actually get zero out of it. Okay. This is a better way of thinking about linearly dependent sets for the purposes of figuring them out. I say not all zero here because, after all, if I was allowed to make every single constant equal to zero, if I was allowed to count that, then everything would always be LD. Because if I was allowed to make all of my constants equal to zero, then I could just put zero for all of the constants here on the left side. What's all that going to add up to? Of course, it's going to add up to zero, trivially, for every set of vectors in the entire universe. So it would not be a very interesting concept if I was allowed to have zero as my solution for all of these constants. What I'm looking for here, guys, is an interesting way to make my vectors cancel out in a linear combination. By interesting, I mean I want to cancel out these vectors in a linear combination without just putting zeros in front of all of them. Okay, so I'm looking for a way to do it without just sort of the what I call the trivial way, where you just kill every vector with a zero as a scalar in front of it. So this not all zero is really the punchline. So we could go back to both of these examples and rewrite them kind of in the way that I've expressed here. So both of these examples were LD. So that means that I should be able to sort of do this. I should be able to cancel those vectors out in a linear combination where the scalars are not all zero. And it's not that hard to do that, guys. So I'll just do this in blue over here. This box equation here, all I'm going to do, okay, so I don't want anybody to think I'm doing anything too genius. I'm literally just going to move everything to one side of the equal sign. So you're just going to end up with a zero on the right-hand side. Yeah, so this is just C1 times V1 plus C2 times V2. And in this blue box, I have my constants, which are 5 and -1. They're not all zero, right? And see, I can do the same thing here. I can do the same thing with this one. I can rephrase this or rewrite it. Let me move everything to the left side. I'm going to take this box and move everything to the left side. So I'll have a V1, and then I'll have to subtract the V2 over. I'll add the V3 over to the left. I'll subtract the V4 over to the left. I already have the V5 on the left, and now I've got nothing left on the right side. So this would be the way that we could then write it. Okay, so the blue boxes that I've now sort of put next to the linear dependencies that we originally circled are more lined up with this approach to linear dependence. But it's really not a big deal, guys. You just take your original linear dependency and move everything over to the left side. So that you end up with equals 0 here and equals 0 here. Okay, and if they ask you to find a linear dependency, these are also just as valid as linear dependencies. So this is a linear dependency, so is this. Any of these equations are showing linear dependencies. Okay, so now, are there any questions here? We're doing great. We're doing great on this. Let's do another one now where we're going to try to use this definition to begin with. We're not going to try to eyeball it anymore. Okay, eyeballing it is not going to work very well. I mean, we got a little bit lucky here. This one was just doable, but you can imagine with a big handful of vectors trying to eyeball a linear dependency is a really kind of a fool's errand. It's just not going to be a good way to proceed. So let me do another example, and let's see if we can figure out how to exploit this rephrasing in a way that will really be useful for us. And in fact, this is where we're going to see the put it in a matrix idea that every single question in Math 250B seems to end up being. So let's do another example here. I'll start off, and this time I think I'll use matrices instead. So let's do this. Is the set, I'm going to make a matrix here, 1, 0, 1, 2. We'll use 2 by 2 matrices for this example. 1, 0, 1, 2, and then the next matrix is -1, 1, and 2, 1. And then my third matrix is going to be 2, 1, 5, 7. And I'm going to ask the question, is this Li or LD? This is the big question that we are asking here in the first part of our class tonight. Is it Li or is it LD? This is the question. Okay, maybe just a little bit. Okay. I want to do it though using this setup. So I'm going to start off with this linear combination down here. I'm not going to try to eyeball anything right now. Okay, maybe some of you can eyeball it and figure it out, but let's pretend that we can't because we probably won't always be able to eyeball it. So let's just set this up. C1 times the matrix 1, 0, 1, 2 plus C2 times the matrix -1, 1, 2, 1, and then plus C3 times 2, 1, 5, 7. So this is just C1 times V1 plus C2 times V2 plus C3 times V3. And now we're going to set this equal to the matrix of all zeros. The zero vector, which is the matrix of all zeros. And the question we are asking is, can we solve for the constants, the C1, the C2, and the C3, without just making them all zero? Obviously, if I let C1 be 0, and if I let C2 be 0, and if I let C3 be 0, then of course this equation is true. That's not what I'm interested in. I'm asking, can we find an interesting solution to this problem? Can we find an interesting choice of C1, C2, and C3? Okay. Well, guys, we actually, if we want to really get our hands on this problem, we can recognize that although it looks like there's only one equation right there in that matrix, there's actually 4 equations up there. Because there's an upper left corner, there's an upper right corner, there's a lower left corner, and there's a lower right corner, and those are each giving us some kind of an equation. So like if I go upper left, so I'm going to actually write them all out. Upper left, upper right, lower left, and lower right. So I'm going to make 4 equations here, depending on which corner of the matrix I'm focusing on. If I look at the upper left corner, you see I have C1 times 1, and then minus C2, and then plus 2 C3, and that's supposed to be equal to 0. That's the upper left corner. See how I'm doing that? And if I go to the upper right corner, I don't have a C1 because there's a 0 there, but then I have C2, and then plus C3. And then that is equal to 0 there. Okay. And then lower left corner, I have a C1. I'm just taking C1 times 1, and then plus 2 C2 plus 5 C3 is equal to 0 as well. And then we go to the lower right corner, And we have two C1 plus C2 plus 7C3, and this is equal to 0. So we have taken our equation and we have put it into a system of 4 equations. Again, guys, the question is just whether or not we can solve for these constants so that they're not all 0. If I allow all zeros for all of these variables, of course it's going to work. All these equations will work. That's not the point, right? The point here is, can we find a non-trivial solution? But you know what I'm going to do next, don't you, Julie? I got to put this into my augmented matrix, right? I told you everything ends up going into a matrix. Let's actually just do that. I'm going to write down an augmented matrix here, guys. The first equation would be 1, -1, 2, augmented with 0. The second equation would be 0, 1, and 1, augmented with 0. Third equation would be 1, 2, 5, augmented with 0. And the last row is 2, 1, 7, augmented with 0. And I'll start circling some pivots right away. Those first 2 rows are looking really good. But I'm going to just do some EROs. Now, the unknowns here are C1, C2, and C3. So those EROs, guys, that we learned in chapter 2, they're not going away, right? We are still going to be doing a lot of that kind of stuff. Let's come up here, and I'm going to leave the first 2 rows the same. 1, -1, 2, augmented with 0. And then 0, 1, 1. Augmented with 0. And let's see. Oh, I shouldn't have written an equal sign. This should be a twiddle. My little ERO notation. And the ERO that I think I'm going to do, I want to get zeros right down this first column. So I'm going to do A13 of -1. See, I have a 1 and a 1. So I'm going to take the negative of the first row and add it to the third row to get that 0 right there. And if I do that, I'll get 0, 3, 3, and 0. And I'm going to also, at the same time, I'm going to do A14 of -2. So I'm going to take -2 times the first row and add it to the fourth row. I get 0, 3, 3, and 0. Now, what you're noticing here probably is that the second, third, and fourth rows are pretty much the same. I can just start crossing them off. I think I did that the other day. I started saying we're going to get a little lazy with this. You can just cross them off. The one mistake I do see people make sometimes, though, I'll see people cross off all 3 of them. Well, you can't do that. You got to save one of them, right? Otherwise, you're losing information. So I can cross off this row and this row. When I cross them off, I'm really saying that they become all zeros as I go on, right? So what do I have here? Here's C1. Here's C2, here's C3, and what you'll notice is I only have pivots in the first 2 columns. That means that C3 is free. So, is it okay if I write over here, guys? You guys can see from way over there. All right, so C3 is free, right? And then if I go back to the second equation is really the same as what we had written down originally here. C2 plus C3 has to add up to 0. So that would tell me by back substitution that C2 should be -t. And then going back from there, I can solve for C1. C1 should be equal to what? C2 minus 2C3. So that would be, well, let me just write it down so we don't mess this up. C2 minus 2C3. C2 is -t, and then C3 is t. So that's -t minus 2t, should be -3t. So here's my question for you. Do the constants have to be all 0? If t was 0, they would be, but does t have to be 0? No, t is free, right? T is free. T could be anything. T could be anything. There are millions of choices for C1, C2, and C3. In fact, I already knew that these vectors were LD the minute that I saw that there was going to be a free variable. As soon as I saw there was a free variable, I'm like, aha, there's a T that's going to be in my list of constants over here, and I'm going to be able to choose freely a value for t. Yeah, right? And so that's the reason I know that these vectors are LD. Okay, not only that, this is actually even better than we might think. We can actually make our linear dependency by just choosing a value of t. So I'm gonna do that here, guys. I'm gonna choose a value of t. Actually, maybe I'll let you guys choose a value of t. Anybody wanna give me a value of t that we could use? There's really only one value of t that you wanna stay away from. Which value of t do you suppose I don't wanna use right now? 0. I don't want to use it. If I use t equal to 0, oh, well, then all of my constants are 0, and I'm not demonstrating the not all 0 business here, right? So, but you can choose any other number, and I recommend just getting in the habit of making it easy. Choose something like 1. There's no right or wrong choice here other than 0. So as soon as I do that, then C1 becomes -3, C2 becomes -1, and C3 becomes 1. And what that means is, in terms of my original linear combination, -3 times the first matrix plus -1 times the second matrix plus 1 times the third matrix should be canceling out to all zeros. Go ahead and put a box here. This, again, is your, or is a, linear dependency. This is giving me an equation that shows me that the vectors are LD. It's a relationship between those matrices. And anybody who's doubting me here can just check it out. Just do the math. Corner by corner, the left side should totally cancel out. Does it make a little bit of sense? Anthony?
Yeah, good question. So does that mean like, it would be linearly independent if A x equals 0?
It would be linearly independent, basically, if there were no free variables here. So you would have to have a pivot in every column. That makes some sense? Okay, guys, I want to try and learn as much as I can out of this example that we just did. Because we're going to find a big connection to something we were just doing very recently. Ready for this? So I'm going to ask you the same kind of question I asked you on Tuesday. Do you see the original vectors from my original set showing up anywhere in the work that we did below? Where are they showing up? 1, 0, 1, 2. Do we see that over here anywhere?
Yeah.
First column, right? 1, 0, 1, 2. Second matrix, -1, 1, 2, 1, and so on. These vectors have ended up in the columns of my A-sharp matrix. Does that sound familiar? It should. Last time, when we were asking about spanning sets, we would have a set of vectors and we would be asking a different question. The question on Tuesday was, do my vectors form a spanning set? And we ended up laying them into the columns of a matrix as well. Now, there was a difference. On Tuesday, we were using this number symbol to sort of augment the matrix with. Whereas over here, you can obviously see that the matrix is getting augmented this time with a column of zeros. But other than that, it's really the only difference. It's really the only difference. What if I gave you a set of vectors and I asked you both questions at the same time? Are they a spanning set and are they Li? Do you realize that for either of those questions, we're going to be throwing the matrix, the vectors into the columns of this A-sharp matrix? It'll just be a difference as to like what you're augmenting the matrix with and sort of what the right-hand side vector looks like. In fact, you know what I think I'm going to do? I didn't erase this for a reason. I'm going to come right back over here. I love this stuff. Can I possibly get more excited about it? I don't know. I've taught it 30 times. I think one of these days it's going to get boring. It just hasn't happened yet. So I just really enjoy seeing these connections. I enjoy seeing these connections. So I have my test for spanning set here. So you know what I'm going to do right next to it now? I'm going to write my test for Li, right? So we're going to throw that one up right here. Test for Li. So let's just compare and see what the differences are, at least based on this one example, right? So what we would need to do is we would need to lay our vectors for this one. We would lay them vertically into the columns of a matrix, and then I'm gonna augment this thing. So V1 up through Vn gets laid out, and then this time we're going to augment with a zero vector. So it's looking similar to this, but the matrix is set up almost the same way. Now this time, I want to decide, are my vectors, you know, Li or Ld? So it's still kind of a, you know, thumbs up, thumbs down kind of question, just the same way that this was a yes, no. Here we're gonna have a yes, no as well. So that, on this problem over here, the vectors were Ld. And I just want to remind us, why were these vectors Ld? Well, it was because as we worked through all this process, we came up with a free variable, right? There was a free variable. So that's kind of bad, by the way. Remember, Ld is what we don't want. So this would be if free variables. If there's free variables, then that's bad. That means the vectors are Ld. You're going to be able to plug in a number for t. You're going to be able to make a linear dependency, and that's not what we want, okay? Li, of course, is just the opposite. The opposite being if no free variables. If there's no free variables. So the issue has changed somewhat. This matrix is for sure consistent, right? Unlike over here where we have the number symbols on the far right and there was an issue, well, maybe there would be a pivot in the far right column. That's not an issue here because the far right column is all zeros. Did you notice that? Every single step, that far right column, I don't care, you could do 5 million EROs, the far right column is going to be all zeros forever. It's never going to change. So it's not an issue. Here, the issue is not consistency like it was over there. Here, the issue is not consistency. Here, the issue is, are there free variables or not? Actually, in other words, is there one solution to this system? Or in the case of free variables, there would be how many solutions? Infinitely many, right? When anytime you have free variables in your system, well, that means you have infinitely many solutions. Yeah, so this matrix here is either going to have one solution, which is the one where all the constants are zero. That's the one we're not interested in. Or it's going to have infinitely many solutions, and that's going to allow you to make linear dependencies, like we just did right here. Yeah,
We
please.
have no solution for Li. Like how we have our pivot point on the opting side.
Uh-huh.
Can we have that?
Can we have what?
Can we have a pivot point right here, right? The zero solution.
Not on the far right column here.
So
So
no zero, huh?
if you have a column of zeros, you will never get a pivot there. So that's why I'm saying this system will always have at least one solution. Yeah. Okay. By the way, so this was a linearly dependent set of vectors. Would anybody have a game plan for me? So in other words, I spent $3,000 on that. And I didn't really want to spend that much money. The vectors are LD. Would anybody have a game plan for me to replace this set with a better set that's LI? Would we need to, like, let's say I wanted to, you know, find a set of matrices that span the same exact thing that those three matrices span. Would I need to like start over from scratch? Try to figure that out, or could I use what's already here? The real problem is this C3 being free, right? Just imagine for me for a minute, guys, what if this column wasn't here? Okay, you don't need to do this in your notes, just kind of watch this for a second. If I didn't have that third column, then would there be any free variables? No, there wouldn't be any free variables, and no free variables would be Li. That'd be good. Well, what would it mean to not have that column? Well, that would mean that we never had this column to begin with. And that would have meant that we had never had this matrix to begin with. Right? Essentially, because didn't we just observe that these three matrices get filled into these three columns? So if you were willing to just go back for a refund and say, I want my $1,000 back on that vector, because it's creating a linear dependency, then these two vectors alone would have been Li. You see that? Essentially, what I'm saying is, guys, we can have a do-over here. If these vectors are LD, all right, get rid of that one, which really means we're getting rid of that, which means we're getting rid of that, which means we're getting rid of that. And now we have only spent $2,000 and we have a linearly independent set. Pretty awesome. That's pretty awesome. Everybody with me?
Well, but does that mean the vector of three, which is erased, is not belong to whatever space?
No, the vector space is M2 of R. Okay, that's just in the background. These are obviously all just 2x2 matrices in V. It just means that this third vector is expressible in terms of the first two, and so it's linearly dependent. That's all we're saying. So, guys, have you guys heard the expression, we want to have our cake and eat it too? I don't know where that comes from, but I remember hearing it when I was younger. Anyway, we would like to have a spanning set for V that is also Li. We would like both, right? That's like a win-win, right? If we can make a spanning set for V, but we want to do it as cheap as possible. And you notice to get the spanning set question answered, we do this setup, this test. To do the Li test, we do this. What you notice though is the two matrices are almost the same. The only difference is the far right column. Over here we have the number symbols. Over here we have the zeros. I sure don't want to do all those EROs twice. I don't want to do them once to answer this question and then do them again to answer this question. So you know what we're going to do? We're going to put them together simultaneously. We're going to do them both at once. I'm going to do another example now. Okay, so let's do another example. And what I'm going to ask you this time is the set, and I'm going to use some vectors from R4 here, 1, 1, 0, 0, comma, 0, 1, 1, 0, comma, 0, 0, 1, 1, and finally 1, 0, 0, 2. But instead of just asking you whether they're Li or LD, I'm going to ask a 4-part multiple choice question, which you will definitely be getting on the next midterm. So this kind of problem is right up there among my favorite, which is I'm going to take this set and I'm going to ask you, is it a spanning set for R4, Li, both, or neither? I want to know everything. I want to know, are my vectors able to span R4? And then are they also Li? Or are they both? Or are they neither? I'd love it if they're both. If they're both, I'm like super happy. I've got a spanning set, which is a good thing, and I've got as cheap of a spanning set as I could get, right? I'd love the answer to be both. Now, I don't want to answer these two questions separately with two sets of redundant EROs. So you know the way we're going to do this? For the solution, we're going to, of course, we're going to jump straight to the A sharp. We're going to jump straight to the A sharp. And what am I going to do? I'm going to lay my 4 vectors into the columns. First column would be 1, 1, 0, 0. Second column is going to be 0, 1, 1, 0. The third column is 0, 0, 1, 1. And the fourth column is 1, 0, 0, 2. And now I have to augment this matrix. Draw a thicker bar here. I'm going to augment this matrix, and because I'm going to try to walk and chew gum at the same time. I'm going to try to do the Li question and the spanning question at the same time. So you're going to see me do this a lot, guys. I'm going to put the number symbol and the 0 kind of with a slash in that far right column, just to tell myself I'm doing both tests at once. I'm gonna do both tests at once, the spanning test and the LI test. I'm gonna do them both at once here, okay? So I still have to do the EROs, but I'm only gonna have to do them once. And maybe you guys would be willing to let me just skip the EROs and tell you what happens. The EROs are getting pretty lame these days. Let's just go straight to the row echelon form here. So if I do that, it turns out that this turns into, the first row stays the same. So I have 1, 0, 0, 1, and I'm augmenting it with number symbols and zeros. And then the second row is 0 and then 1, and then 0 and -1. Again, augmented with number symbols and zeros. The third row is going to be 0, 0, 1, 1 when I get it into row echelon form, augmented with number symbols and zeros. And then the last row turns out to be 0, 0, 0, and 1. Augmented again with number symbols and zeros. Okay, so it's going to look kind of like that. It'll look kind of like that. Remember, as you're doing the EROs, the column of zeros stays as a column of zeros forever. It's never going to change, right? If this column of zeros on the far right, I don't care if you permute or if you add a multiple of one row to another or whatever, that far right column is just going to stay column of zeros forever. And the same thing for the number symbols, right? If you have a column of number symbols and you permute 2 rows or add a multiple of one row to another or whatever, it's just a column of number symbols again. So what I'm trying to say here, guys, is that what's going on to the right side of this bar is totally nothing. It just stays the way it is from the very beginning. You're really just working on the left side. You're really just working on the left side. Now, based on this row echelon form, I would like to know what's the answer to my question. Is it a spanning set? Is it LI? Or is it both? Or is it neither? Is it consistent?
Yes.
Consistent is yes, right? Because there's no pivot in the far right column. And are there any free variables going to come into this? Not at all. So that means no free variables means LI. Guys, it is both. It is LI and a spanning set. This one is both. This is as good as you could do. $4,000 in order to span R4 as cheaply as possible. That's exactly what that example has done. That's exactly it. Okay. Right. Well, I feel pretty decent about that. This one over here, if I had asked this question, obviously it's not both, it was LD. I guess I erased this matrix. I guess I should go back. We still have the work on the board. Well, sort of. What did I have here? This was, oh dear.
I got it. 2, 1, 2, 8.
2, 1,
3,
3, 3, something like that. Looking at this, what would you have answered? Would you have said it's LI, spanning set, both, or neither? So we already know it's LD, right? We can see that there's a free variable here. My question is it consistent? Do we get a pivot in the, so if I was to go back and put number symbols, because now I'm sort of doing both questions. If I had done that, right? That would be the question. So these bottom 2 rows would have become all zeros, right? If we had done our EROs properly. So my question is, with respect to the number symbol part, would we have a pivot in the far right column? Right there. We sure would have, right? That third row is 0, 0, 0 number symbol. So this one is neither, right? So we've gone from both here. On this example, it's neither. Do you just see how important the pivots are to everything? Right? Where those pivots end up is really critical to whether the system is consistent or not, as well as whether there are free variables or not. So, so everybody kind of got the idea here? So this is linear independence. We're going to keep practicing it. We need to do a little bit more, I think. Actually, after we take our little 10-minute break, turns out that when you have both, when you are happy with both the spanning and the LI, you have a really special set of vectors. And they are called something called a basis for the vector space. So I'm going to define that and do much more with examples after we take a little break. But it's about 5 o'clock. Why don't we get some downtime for 10 minutes or so? Let you guys go outside if you want to, stretch your legs. Hey, it's still light out. After 5 o'clock by mid-semester, we don't have to stand in the dark all night. So feel free to take a little break and then we'll just pick things back up. Yeah, what's up? Yeah, they're gonna just be, if we kept going with the arrows, this would have been 0, 0, 0, 0, 0, 0. But crossing them off because they basically are
Yeah, we
worthless.
could have added two,
Yeah.
4 times.
-3, yeah.
And then to have 0. Oh, okay.
Okay, great.
I was looking at the other road.
No problem,
I got
no
it.
problem. Yeah.
Still not scalar multiples, or is
If
it like a
it's-
strict stipulation?
No, this works both directions. So if these, I could have phrased it differently. I could have said these vectors will be LD if they are scalar multiples of each other. If and only if they are scalar multiples. Yeah, so that's really what
Okay.
the rubber hits the road is, hey, are they scalar multiples of each other or not?
Yes.
Thumbs up or thumbs down, that determines whether they're LD or LI.
Okay.
Yeah, that's it. The bad thing about that little remark there is that it's only when you have just two vectors. So I wouldn't be able to use it here.
Right.
Like you could look at this and say, oh, these aren't scalar multiples, none of these are scalar multiples of each other, right? No two of these are scalar multiples of each other, but you can't use that as a reason to say they're LI.
Right.
They could actually be LD without having any scalar multiples
Gotcha.
when you have more than two vectors.
Gotcha.
Yeah, that's the deal. Yeah. So. Did I? Oh, okay, yeah.
Sorry, I wrote it down.
Okay.
He's saying that.
Yeah.
Says I don't have number 6, and I don't have.
No 6 and no 28.
And
And they're right there.
Yeah, they're right there.
How we missed that? Can you,
You want me to like this?
please, yeah, would you? Because right now, in the middle of class, I'll never remember that, but I will.
Comment on this.
You can do it either way. I'll get notified either way. But I'll definitely take it. I'm sure that you did that. Yeah, that's no worries. Yeah, I'll fix it.
You had to say
It was brutal.
Yeah.
So today, I went like 8, I was studying for my exam. For me, same as Tuesday. Yeah, not spending my day here. That's what I go for, and I have my 11% skill.
Yeah.
It's much fun. That I haven't started yet. I haven't even downloaded it yet on the and just work on it. Get the secondary for I have my own laptop, but I got see what
That's like an iPad, but like it's a Windows.
So that's work on it.
Yeah. Is the last one gonna be like that? It's like the last one, it's like an assault. You just make it into a tablet, so you can, it's like a neck, you keep it.
But then have I used this device?
That's reminding you of that.
So look, yeah, I never used my months and then I started using notes on it because one of my classes, I don't wanna like, have a physical copy of like print out.
That's-
How
I'm
about
saying
that?
that would- If I would have it on side and if he messed up. He both, but I promise.
He's only instructor for that business.
That was random.
Oh, I hate when it makes
You didn't use a single one.
I should make sure my next practice exam has nothing to do with that.
Oh,
You guys know.
And
That's why you really like that.
No.
Okay.
Okay, you know, actually, you know, everything, and you simplify it to where it is.
I try.
And your best compliment.
I do my best I possibly can. What class is this you're talking about?
Physics 227.
Oh, yeah, I don't know.
What's the professor?
Go ahead, probably know.
Yeah, who wants to volunteer?
I probably already know who that is.
Yeah.
Start with a W. No, that guy might be trying.
Gary.
Who is it?
Gary. Oh man, now you're doing. Yeah, like at this meeting. No, because he walked around. So he turned to, I was in there when he came to tell us like, he was like, it sounds really straightforward. It's a little like old, like, I was like, the hardest test I've ever taken in my life. Physics after. And then like, Gary was like so confused, he's like, I was like such a straightforward test. What? Anything, I was anything closer to the test. Not included.
Whatever it's done is.
Yeah. Regardless of how you do. Oh, he said this. 1 out of 3. 1 out of 4. He said this on Tuesday. The lecture before the exam. Like, no, like, it's an exam. I'm the first curve party. Let me record.
Figure it out here for you guys. Oh, okay.
Sorry. That's what.
Final.
So these are done with that. Oh, wow. Well, that's a good, way to go out of an econ.
I think so, yeah.
That's only my 6 o'clock class.
All right.
I knew so. I started doing it Thursdays. Same for me, but like, I don't want to stay here.
Dude, if I don't start locking in, I'm gonna like hard.
It's all, it's gonna be wrong. Yeah, I still, I get it, it's good.
That's why, yeah, get started like done.
Good stuff when you guys are young, yeah.
I have 5 days.
So 3 of 3. Wait, that's Friday, right? You're 3 Oh, 2 of 3. Next. 3 of 3 and 3 of 3. The lab is only on Friday.
If you guys all had a test today, I guess it's really good we didn't have homework for this class. It's kind of nice. The timing for that was good. Awesome. If only the professors would always coordinate it better. Yeah, man. Half the time it doesn't happen that way. Like everything hits in 1 week.
Oh my God, don't say that.
You're hard.
Guess you're doing okay?
Yeah,
No worries. I am too. I'm usually very tired on Thursday night. So then I don't have any classes on Friday or Monday. So.
You don't want to.
Yeah.
Sounds like. Oh, we can get a second. He's good.
He's good, man. But he's. You would, you know, do some bargaining. All right, guys, I think I might go ahead and get us back together here again. I think most people have made their way back in here. I passed out a group work, and in a minute I'm going to have you look at it. You can kind of see problem number 2. It's got the four parts. You know, does S span V? Is it LI? Is it both? Is it neither? So you're going to get in a few minutes. I'm going to have you guys try a few of these with your classmates in groups. But let's just do one more just to make sure we're totally understanding how this all shakes out. I've got an example here for us to look at just to keep practicing what we've been doing. This is a set of, this time it's polynomials. So we have the set 3 plus x, 4 minus 2x, and 6 plus 3x here. And I'm going to ask you the same 4-part multiple choice question. Is it a spanning set for the vector space? By the way, the vector space would be P1 of R. You can notice that these are polynomials of degree 1. Or is it Li, or is it both, or is it neither? Okay. So what am I going to want to do first? Put it in a matrix. Exactly. And the only thing we have to do is make sure we put it in the matrix correctly. All right. Each of these vectors, maybe I'll label them as V1, V2, and V3. Each of them goes into the columns here. But as I make these columns, of course, I'm not going to actually put the x's into the matrix. I'm just going to take only the coefficients. So here I have a 3 and a 1, right? So there's a 3 for a constant term and a 1 for the x. Okay? And then for the second polynomial, I have a constant term of a 4, and then the x coefficient is -2. And then on the third column, we have a 6 and a 3, right? By the way, sometimes students will ask me, well, do I have to do the constant term first and then the x term? Like, so you notice I started on the first row, I have all the constant terms, and on the second row, I have all the x terms. Turns out you don't have to do it that way. You could have made your first column to be 1, 3 instead of 3, 1. The only real caveat with this is that whatever order you're going to list the coefficients for the first vector in, you must then follow that same order for all of the other vectors too. You can't switch halfway through. Okay, but yeah, so there's more than one way to set up this matrix. And then in the far right column, what am I going to augment this thing with? 0 / hashtag. Exactly. It could be zeros or hashtags, right? Exactly. So I need to get this thing kind of into row echelon form. I should probably start by permuting the 2 rows so that I can get my pivot, which is a 1, into the upper left corner there. So I'll have a 1 there, and then the second row is filled in with what was the first row before. Okay, so we'll do that, just swapping the two rows. And then finally, I'm just gonna do A12 of -3. So I'm doing this fairly quickly, but because of the 1 and the 3, I need to make that 3 into a 0. So I'll do A12 of -3 now. And so the first row stays the same. And on the second row, when I multiply by -3 and add it to the bottom row, on the first row, let's see, so then we'll get a 0, and then -3 times -2 is 6. I add 4 to that, and I'm going to get 10. And 3 times -3 is -9. I add 6 to that, I get -3. The far right column is just sort of turn off your brain and just draw your 0 number symbol thing. And I'm going to go ahead and circle this pivot right here on that 10. It's not technically a pivot, but the position of that 10 is where the pivot is going to be. Based on what we have here, guys, can somebody tell me what is the correct answer to, let's go back. Based on this, we should be able to answer the question. Is it a spanning set? Is it LI? Is it both? Or is it neither? Maybe let's take a vote. Okay, raise your hand if you think this is a spanning set, only a spanning set. Yeah. So spanning set only. 3 people. Okay, 4 people. How many people think it's LI? Just LI. Okay. A lot of you are not voting so far. How many think it's both? Okay, we got 4 or 5 people who think it's both. How about neither? It might be the majority. Maybe the majority is neither. So let's talk it through. Let's start with the spanning question. The test for spanning, as long as there's no pivot in the far right column, right? It's a yes on a spanning set. Is there a pivot in the far right column here? Over here? No, the pivots are just here and here. So it is a spanning set, okay? What about LI? Well, for the LI question, it comes down to free variables. Do I have any free variables here? Pardon me? The last one, the last column here? Okay, I'm not going to remove anything. I just want to know, do I have any free variables here? I do, right? I do. This third column has no pivot. So if there's a free variable, guys, it is LD. Free variables means LD. So it's not LI, but it is a spanning set. So the 3 brave people who raised their hand on the first time I asked actually had it right. It is a spanning set only. It's not LI or anything else. Okay, does that make some sense? You might notice something about this, by the way. Actually, by next week, you're going to be able to look at this set of vectors and tell me without even taking a breath that it's LD. You know why? Because this matrix is wide and fat. And if you have 2 rows here, the most number of pivots that you could have is 2. But how many columns do you have? 3. So can you have a pivot in every column? Not if the matrix is wide like this, right? Because basically you have too many columns. So if you realize ahead of time that your matrix is kind of this shape, where it has more columns than rows, then you even know before you even start thinking about the EROs that you're going to have a free variable, and these vectors cannot be LI, right? But really what it comes down to is that this vector space P1 of R is pretty small. It's pretty small, and spending $3,000 in a vector space that's this small has got to be too much. It has to be. There's too many vectors there. So yeah, we'll be able to, we're actually going to learn by next week how to take this 4-part question and be able to cross off 2 of the wrong answers immediately without even doing an ERO. In this case, the 2 wrong answers are it cannot be LI, and of course, therefore, it cannot be both. Because it can't be LI because there's too many columns, right? So this one, the only thing we really had to do is kind of check, is it a spanning set? That part, I admit, we would have to go through this work in blue here to answer it. Make a little bit of sense? Everybody okay with that? Even the folks who maybe originally didn't think it was the first answer? Anybody want to ask me anything? Okay, if not, guys, let's take a few minutes, probably not the entire class, but let's take a few minutes to grab 2 or 3 partners that are anywhere you want to work. There's whiteboards all around the room. I'd like you to take a look at group work number 7. And I'll come around and give you a hand. These are, and you can start with problem 2 if you want to. I don't really care where you start on the handout, but see if you can do those 2 problems. Actually, quick comment. You could kind of skip over 1A. So if you're going to do problem 1, just go straight to part B. Try to find a spanning set for it, and then work on problem number 2 as well. So have at it. There should be markers everywhere around the room. Just turn around, find some folks to work with, and I'll come around and help you.
Actually, yeah.
The handout? Yeah, grab it out of that. Come on down.
Yeah, sure. Something that would say.
Anthony, aren't you working with somebody? Nathan, do you have a partner? Okay, that's fine. Aaron, do you have a partner? Go hop in with them. Anthony, could you do a hop in with this group in the middle, please? Is that okay? I would appreciate it, because you can help. I know you know this stuff. Thank you. Vinny, how about you?
Oh, yeah, oh.
No, I want to have you working with somebody. Why don't you work with each other? Let's talk to each other. Do you have a group seat? Why don't you join these guys? Okay? Guys, I'm gonna have a few people join you, so we're gonna be like a nice big group here. I want everybody to talk and exchange ideas here. Oh, wow.
Yeah, so it'll be, yeah, because it's,
That's the right.
oh, yeah, so the next, right? Yeah, so the.
So that'd be negative one. So it's delayed.
Oh, yeah, 0 negative.
That's what we were talking about here tonight.
Oh, yeah.
So the finding expansion, that's a different thing. That's where you write down the form of the vector that you're looking at. Bust out the variables, and then we list your we list the for the vectors that are that's what we're doing.
Yeah, so I was pretty good with those 2.
All right, let's see how we're doing that. Already have the matrix set up. Nice. I have another idea. What size?
No, we don't have some water. Like, it's gonna be in the house.
It's not a verbal, there's no. Okay, you guys are that, you're doing fine, right? So you set up some, doing pretty more over, I don't mind that. So we take 28 times 4. Question 2, see how we're doing. So this is kind of spanning that thing. Really.
Oh, okay, guys, you have a lot of ones.
That's it. Never form. So step A was right down over the record. It would be step B is variable. That's the variable, right? And then step C was.
Because it's not.
Just list the agencies that are left over after this. Next step is the bus stop.
Looks good.
I need to be a little cautious here. Cross off this bottom row, and that is all fine and good over here. So this is going to be 0, 0, 0. When you cross it off, you need 0. Listen, this has on the right side, never changes. This actually is a pivot in the far right column. Anytime you cross it out, so. Pardon me? Anytime you cross it out, you just cross out the matrix. Yeah, don't cross off anything in the far right column. I probably did that accidentally earlier. Yeah, you don't want to be crossing all the way to the far right. Yeah, exactly. Can you guys explain this? What you just read from me a little bit? Give it one more drop. Okay, thank you. I'll let him explain. Yes.
One or two free, but not free by one.
This one you have one free variable, right? So this is a pivot, but here is a free variable, right? So this is what that means LD, right? And then the pivot here means no span. So this is a really lousy set of values, right? They didn't span the space, which is what you wanted to do, and you pay too much money for them anyway, right? They're LDL, so it's a bad set. It's a neither. This one is a neither.
Okay, so.
Okay.
So what we did is.
How we doing, gang? Except that you don't need that number symbol. But problem is after we find a spanning set, actually was what we were doing mostly. So you write down the form of the matrix.
And then, in the reset is neither, it doesn't.
And then that was what on Tuesday, I got step on the far right.
On the far right.
Yes. Very nice. So yeah, now you're putting the plus out here. And then you're gonna make your. Maybe you can help.
So then 15, it would only span if there was insufficient ordinance.
Talk to each other, because you're all getting on the same page.
Take us. Just go ahead.
Just like that. Yeah, it's a book.
Do you guys want to try?
You bet everything.
Yeah.
So I'm gonna just make a comment on it here. Because of that. You'll say you have to do all these arrows. You could just use the arrow method on your resume. This is not wrong. It's not wrong. And you're actually doing pretty well here. And you can actually just see second and third. No. I can't bench.
Yeah.
I'm just telling you, you could have got
That's-
There's a little less pain and suffering if you would just. Something to keep in mind.
No, because I think that's not. So in this case.
Yeah, yeah. Measures.
Five, so it's gonna be 5 columns. And 4 rows. Four pivots. Like any variable, so it can't be. It can't be any of these now. So. So we gotta work it out to see if that's.
The important thing here, and this one crosses off, right? But the important thing here is all the way over here.
I took it last.
Yes, it's gonna be. Right.
No, it's not.
This is
That-
really
the
hard.
bunny bus
Right.
I decided.
Oh, that's a good.
Second row.
And then the number that I came here.
Yes, I think you just go. Positive 2 line.
It has to be the same for everyone. Oh, sure. Yeah.
There's only 3 minutes. But now. These 2 cancel out, right? That's just saying it's like.
I draw this. Is everybody needs help?
Yeah, so that would be 0, but this thing.
So.
Guys doing okay?
Yes. Yeah. Oh, there's that one. I would find like.
Exactly. You're gonna have a free variable even before I take a breath, I know that. So I can see even without even doing any work, that $5,000 is too much money. So it's LD, and then the spanning part, you've got this row crossed off, but of course, as I talked about before, that's really a pivot. Yeah, so this is another bad set of vectors. It's neither. It's not a spanning set, it's not a line.
I have a question. So when you cross out a row, does it automatically put a pivot on the right side of? I guess.
Remember that our pivot is the first non-zero entry. When I'm crossing off the row, I'm really saying that those are really all zeros. Okay, but the number symbol is like, it's like built out of steel. It doesn't ever get changed. So even if you cross off a row, you gotta still put that number symbol there. And that becomes your pivot. And it's in the far right column. All right, that's what we don't want. That means it's not a standing cell. Okay, great, great, great.
20.
Let's see. You guys get this figured out? You guys did. Sort of multiply that.
Here you get.
You don't have to do your. Normally you would do arrows, right? There's something about that particular matrix that made it nice. Maybe do something different instead. Maybe a little in the matrix is like the square size.
You know what I mean?
Yeah. Yeah, the determinant, just use an arrow method or something. And let's find that determinant. Yeah, that might actually save us from having to do the arrows on this problem. Normally.
Oh, no, now see.
Give it a try. Anybody need help? Did you guys finish? Everything's finished?
That's what I heard.
I don't like what you're doing. If it's a square matrix.
Oh, yeah. You multiply by zero. No, C times B. Yeah, this.
But I think when you were talking about it says for sets, you know, when there's more than one. Oh, because I was thinking like this. Where like you add the A, B, and C. Yeah.
You got zero, so if you got zero, what can I pass it to me? Oh, yeah.
Wait, so like this.
Oh, it's gonna be good because it's right there. Yeah.
That's it. Oh, yeah, they were.
Good job.
Yeah.
So basically, from here to here, like you can split it up. So like, you take out A from each, like from each variable, you can take out an A.
It's supposed to be.
You have to do this.
Or I mean, like, do you have to do this?
Yeah.
Yeah, no.
Okay.
Oh, you don't have to.
It would just make more of them.
Yeah, it's make more of them.
Oh yeah, I remember.
Yeah, you don't, yeah, I guess you don't have to do that. Cause like in this one, there'll be.
It's really good sauce.
Just have one like for A, B, C, like coffee. Yeah, you have to. It's not like. Yeah, you're basically that. There's a lot of ways to get it. That's good.
Let's keep that.
Yes, at that moment I was trying to.
Yeah,
But not in our part, right? So it's not going to.
It's a good question. I don't know, like. But it's.
What's going on?
It was.
Do you get a term? I don't.
Yeah. Right on the height.
I know what the problem is. Oh, because I see. Let me have you some around there. This is actually a major. When you wrote those vectors in the columns, the first polynomial.
Oh, cause like.
Oh, did we write it down?
Minus x squared. Oh, so yes. X squared, constant, right? Oh, x squared is there. Right? Yeah. The next one too.
Yeah, equals there.
Negative 13. So that's gonna take. Oh, well. I would probably at this point, I'm gonna just tell you, if you use the arrow method, you're gonna get a determinant.
We're gonna have a three variable.
Now, that means if the determinant is zero, it's not a verb. But in terms of this question, what am I going to say?
0, 0, 0, 0, 0.
Because it's not going to be consistent, so the idea is if the determinant is zero, then if I did my ER I would eventually find out that I'm gonna get a row. I'm doubting myself on how it makes like that. So you would end up over here, circling this pivot in the far right column, all right, that's not good, right? And then your only other pivots, we've only got two others,
Right.
you're gonna have a free variable. That's also a red flag, right? That's not a foul.
And then you didn't hit the
So it turns out that the matrix is square. I'll take break this down next week. But you just take the determinant and it's equal to zero. Either, like we are here. And if it's zero. Because if it was not zero, if the determinant of A was not zero, then the matrix is invertible. And that would mean that you would get pivots all the way down.
Yes.
Yeah, so there's no free variables and it is consistent. That would then be, it's just gonna be equals. Exactly.
Yeah. We're gonna here. It's just back to housing.
Inside of the square matrix.
And who's that professor across the?
Even if he doesn't like to use the term, that's not, it's the San Francisco State. Downward determinants. But as you can see, we're making good use of it.
Take it out right here.
Yes, yes, yes.
Yeah.
So what is the?
That's what I was asking, it's just 2 minutes.
Oh, yes.
Thank you. Hey, guys. You know what? You've done a great job on the group work. It's about 2 minutes until the end of class, but I know some of you are done. I've decided I'm not gonna try and do anything else tonight. I'm just gonna let you call it a day. So whenever your group is kind of feeling reasonably good about the group work, you're welcome to go. If you do have any questions for me though, I'll be here. You can ask me anything you'd like to ask before we take off. But thanks for a great meeting. We'll look forward to seeing you again next time.